Hello again! Are you doing research involving time series data and trying to figure out which statistical models may be useful for forecasting future values of the time series? My name is Jimmy Lepping. I'm a psychologist and statistician with an interest in various research topics including psychology, education, financial markets and time series data. And in this video, I discuss and demonstrate the option of using part of your time series data to compare the forecasting potential of different models. Here you see an example of time series data from the financial markets, the monthly closing price of copper in US dollar since the start of 2001 until the end of 2023. Suppose that you have some understanding of time series models and are trying to figure out which of a series of models are potentially useful for forecasting copper prices in 2024 and forward as more data come in. So what I'm going to propose in this example is to split the data set in two parts. The first 20 years or 240 months on the left of the vertical dashed line versus the last 3 years or 36 months on the right of the vertical dashed line. We've already got the 23 years or 276 months of data, but for comparison purposes, we pretend for a moment that we only have the first 240 months of data, and we'll use that series to forecast the copper price in the 241st month, hence January of 2021. And although there are many different types of time series models that may be of use for this task, I'm going to limit myself to one family of models, which is also called the Autoregressive Integrated Moving Average Models family, or abbreviated ARIMA. Without going into too much mathematical detail, three of several parameters that can be important in ARIMA models are P, D and Q, where P represents the autoregressive or AR component, D represents a difference component, and Q represents a moving average or MA component. I'm not going to explain these components in detail. There is a lot of literature on that elsewhere, and it's not the purpose of this video, but I'm simply going to compare different combinations of P, D, and Q with the key question: which models perform relatively well in terms of forecasting? So just to return for a moment to the original data set and proposed data split approach, we use a series of 240 monthly data points to forecast the next data point in the series. The reason for proposing in this example to use 240 monthly data points and not, for example, 50 or 60 is that with more data we tend to acquire more accurate estimates for different model components. And for the example at hand, using only 36 iterations of prediction or forecasting will be easy to visualize. But one could, for instance, also choose to let's say use 15 years of data points for future forecasting and hence 8 years on the right of the vertical dashed line for comparison. Now, in this example, we have 36 data points to be forecasted, and for each data point on the right of that vertical dashed line, we use the previous 240 data points to get forecasts. When we do that, we can calculate for each of the models under comparison, for example, of what percentage of difference from the actually observed value, with a negative value indicating that the model underestimates the actual copper price, and we calculate a range of statistics on which these models are compared. And one of the reasons why I use the percentage of difference from observed is that in investing and trading in financial markets, we generally tend to think in percentages of difference rather than absolute differences in any given currency. So the first thing that we see here is that there are two models which demonstrate terrible performance. And these two models are now shown in red. Each of these two models consistently underestimates the actual copper price, and also they have standard deviations that indicate higher variability for these models than for their better alternatives. In short, these two models in red are kind of useless. The other two models, the other 6 models have in common that they use either an autoregressive component P or a difference component D or both. So it seems that at least one of these components, P or D or both, is needed to provide better forecasts. Now the values that are marked yellow here indicate mean and median values closest to 0, which in combination with their standard deviations indicate that although there is variation in performance from month to month, sometimes overestimation, sometimes underestimation, there is hardly any tendency towards under or overestimation, systematically speaking. And when we take the model which has both a mean and median close to 0, marked in yellow, we see a chart expressing actual copper prices and forecasts for the series of 36 months like this. It shows that although depending on the moment in the time series there may be more or less of a difference between observed price and forecast, in general, this model does a reasonable job in forecasting copper prices. Again, the family of models that I use in this video is just one of the types of time series models that one may consider. And to keep the video short, I have not included other combinations of P, D, and Q as well, which are possible with ARIMA models. But I hope this video helps to understand how you can split a time series dataset in 2 parts to compare different candidate models in terms of how they perform. One of the reasons why I decided to make this video is that sometimes I see people try to obtain a model that fits the observed data as well as possible, but if they were to use that model for forecasting, it would fail badly. And in the end, what we try to do with statistical modeling is not just to fit just any pattern, including noise, but to understand phenomena and, where possible, make useful predictions or forecasts. Having said, that's it for this video, which I hope is helpful. And if you have any ideas or suggestions for future videos, just leave a comment below this video or contact me via the email address shared in the description below this video. Thank you for listening and see you soon.